Welcome students to today's lecture. We are still continuing with the terminologies used in thermodynamics. So we have heat. Heat is defined as the energy crossing a system's boundary because of temperature gradient between the system and its surrounding. Heat is represented by a symbol Q. The interaction at the system boundary is only due to temperature difference, where heat is transferred from the hot system to the cold one. Heat is therefore a transfer of thermal energy which crosses the boundary of a system due to the difference of temperature between the system and its surrounding. So the sign conventions that are used for heat transferred into a system is positive and heat transferred out of a system is negative. Heat is a path function. It is a function of a method in which energy is transferred between the system and the surroundings. A process in which there is no heat flow across the boundary, where Q is equal to 0 or heat is 0, is termed as a diabatic process. So let's investigate the first law of thermodynamics, and that is the 0th law of thermodynamics. So consider two bodies that are in contact with each other. One is hot, the other is cold. Heat will be lost by the hot body and gained by the cold one until a point of thermal equilibrium is reached, when the temperatures of both bodies will be equal. The 0th law of thermodynamics gives the scientific expression of bodies in the state of thermal equilibrium and states that if a system A is in thermal equilibrium with a system B, such that the temperature of A is equal to temperature of B, and if the system A is also in thermal equilibrium with a system C, such that the temperature of A is equal to temperature of C, then system B and system C must also be in thermal equilibrium. So the temperature of B must be equal to temperature of C. It is therefore possible to compare the temperature of two bodies by use of a third body, typically a thermometer, without the two bodies being in physical contact. So that is the 0th law of thermodynamics, which thus forms the basis for temperature measurements. Let's now get into first law of thermodynamics. The first law of thermodynamics is also known as the conservation of energy principle and provides a basis for studying the relationship between or relationship among various forms of energy and energy interactions. The law may be stated as energy can neither be created nor destroyed during a process, but it can change form. So let's look analysis of a closed system where there is non-flow energy equation. So this is called non-flow energy equation. For a general closed system, the first law of thermodynamics may be stated as heat minus work is equal to change in energy, and the expression for change in energy can either be the internal energy U plus the potential energy, which is represented by mass times gravity times the elevation Z, plus the kinetic energy, which is a half times mass times the speed squared or the velocity squared. That is, the sum of work and heat interaction in a closed system is equal to the total change in energy in that system. Often, change in potential and change in kinetic energy are negligible in closed systems as compared to change in internal energy, and the first law then reduces as shown in equation 1.2, where you have heat minus work is equal to change in internal energy. This equation is also called the non-flow energy equation. The units of the energy terms are in joules, or more commonly kilojoules. The equation may be expressed in terms of intensive properties. So in terms of the intensive property, we divide all this quantity by mass. So when you divide Q by mass, you get a small q. We designate that by a small q, and W, which is work divided by mass, we designate that with a small w, and internal energy U divided by mass would represent that with a small u. So that is expressed in equation 1.3. So the extensive properties like the internal energy are converted into intensive properties, where we represent them by small letters as represented in equation 1.3. The units of the energy terms are now in joules per kilogram, or more commonly kilojoules per kilogram. In terms of differential changes of a system, a small change in heat minus small change in work will give you a small change in internal energy. So the extensive property change of heat minus extensive property change of work will give you extensive property change in internal energy. So the use of the delta for Q and W and the normal differential D for U is to distinguish between an interaction across a system boundary and a change of property within the system. If the internal or potential and kinetic energy are restored to their initial value by the heat and work interaction, then the right hand side of the equation becomes 0. Hence, for a cycle, the total change in energy must be 0. So heat minus work is equal to 0. This is the statement of the first law of thermodynamics for a cycle. So we can take an example here, which is in a certain steam plant operating in a closed cycle. The turbine develops 1000 kilowatts. The heat supplied to the steam in the boiler is 28 kilojoule per kg, and the heat rejected out by the system to the cooling water in the condenser is 2100 kilojoule per kg, and the feed pump work required to pump the condensate in the boiler is 5 kilowatt. So calculate the mass flow rate of the steam around the cycle. So here you need to know heat that is added to the system and heat that is taken away from the system, and the work done by the turbine as 1000 kilowatt. So if you had 28 minus 2100, then you subtract it from 1000 and you divide by 5 kilowatts. That will give you 1.421 as the mass flow rate. So that marks the end of our today's class. Let's meet again in the next class, students.